Next section is the uniform depth of the channel flow. Water depth doesn't change with the distance for the uniform flow. dy with dx is 0 and the channel slope is equal to energy slope. For uniform flow approximation, flow with constant depth and cross-section area A. So that is a cross-section area of the flow. And the other parameter we call the wetted perimeter. P is the length of the perimeter of the cross-section in contact with water. So that is we can draw, this is the wetted perimeter is the length of the contact area. Okay. For velocity distribution across the cross-section in the non-uniform flow, maximum velocity is far below the surface. Okay, that is this one is show the cross-section, and this show the contour line of the velocity, and this show the profile of this. We can see that the velocity maximum is below the surface. This figure show the cross-section in the pipe flow is not full pipe, and then is the velocity maximum velocity is below the surface. And water velocity is 0 on the wetted perimeter. You can see that this close to the surface is velocity is 0. And that point where the wall shear stress tau W is developed again. And wall shear stress is vary at this figure, okay, for the wall shear stress distribution. Next topic is the Chassis and Manning equation. Okay, if we draw the control volume of the uniform flow like this, is a profile of control volume, the length L. Okay, and we apply the change of momentum, summation of force equal to the change of momentum. In this case, because of the V1 and V2 is equal, so this V1 and V2 is equal to, that is mean the momentum doesn't change. So we can say that the summation of force is equal to 0. So next, what we substitute how many force we have. So we have F1, F2, F1, F2, and that is the shear at the bottom, tau PL, and this is the weight, W sine theta in this makes that equal to 0. And for uniform flow, depth is equal and F is equal. So we can get equation of the shear stress, wall shear stress based on this. Next, if the channel slope is very small, sine theta is equal to tan theta or equal to S naught. And the next, we substitute the weight of the water is equal to gamma AL. You can see from this is the volume is the AL, and for the weight is we just to multiply by gamma AL to get the weight. And for the hydraulics radius, A over P, okay, that is to do one more parameter is A is area and P is wetted parameter. The ratio of A and P is called the hydraulic radius. And so we got this equation. The shear stress is gamma RS. Okay. Next, most of the flow in the open channel flow is turbulent flow. Shear stress depending on the dynamics, pressure, rho v square over 2g not depend on the viscosity. So another term of the wall shear stress. And if we make the K is constant, okay, depending on the pipe roughness, and we make this equation equal between two wall shear stress, and we can come up with the Chassis equation. V is equal to C square root hydraulic radius times the slope. So S is the Chassis coefficient defined from the experiment, but it's not the dimension coefficient. Is unit is about length power 1/2 per time, or square root of the acceleration developed in 17th century by the Chasey. And another equation we call the Manning's equation is proposed by the Irish engineer in the year 18th century. And this Manning equation, V is equal to kappa 1 over k kappa over 9n and radius power 2 over 3 and slope power 1 over 2. That is the Manning equation, and for n we call the Manning resistance coefficient. In this case, k is equal to 1 for the SI unit. Okay. And for friction factor, we learn from Darcy-Weisbach equation, and n, Manning n, related to the wall shear stress at the constant surface. Manning n can be explained in form of F, and this below table show the equation of n. You can see that for the flat plane, n is very large. If the flat plane is full of the tree is 0.15. In the national channels, is major river, the n is about 0.035. Okay. The uniform depth example. The main parameter involved in the uniform depth open channel flow are the size and the shape of the channel. Cross section is area and radius. Slope of the channel is not, and material lining the channel bottom and walls is n parameter, and average velocity of the flow V or Q, what that is, and determination of the flow rate of a given channel of the flow with a given depth. So we call the depth is normal flow rate or normal depth for Yn. Next, I will show you a clip about the open channel flow. This is a channel in the hydraulic labs. It's a merging of the two river. On the right hand side is the small river flow with the red color and mixed with the main channel on the left hand side. We call the tributary of the channel. Okay. Okay. Another clip show the uniform flow. That is a flow in the irrigation channel is a trapezoidal shape and lining with the concrete. You can see that the cross-section area is uniform. Okay. It's for the gutter rain to drain, for gutter on the roof to drain the rainwater. That is the open channel flow in the river. You can see it's uniform flow because of the this one is the in hilly area or in the stream, so we expect the flow is more turbulent in what we call in headwater in highland. Okay.